for the rent. Yeah, but also Kubernetes has the Huh?
Maybe you speak a little louder for the people.
Okay. Okay, that is the ground. Local effect from boundary layer part. Main thing is the local from boundary layer in the code example for understand the interaction between inner and outer layers. So strong interaction between from boundary layer. So when you have to see the effect of local from boundary layer and from internal floor, motivation is constant wall symmetry hypothesis. That is the outside lockness sublayer very close to the wall. And total motions are independent of wall lockness sufficiently large less than that is not constant wall symmetry hypothesis. There are many data. As you can see, even outside lockness sublayer, all data is collapse to similarity, that is we call constant wall symmetry hypothesis. So, Michael Schultz and the current flag and many people did experiments. Many kinds of three-dimensional lockness, messy or sandpaper, and many kinds of geometries of three-dimensional lockness. And they found all data satisfy constant wall symmetry hypothesis very well. So, just within local sublayer, some changes by localness, however, outside localness sublayer, all data collected. However, when I talked about, he selected this geometry, two-dimensional load lock on the wall. Very simple. That is mechanism to compare numerical simulation. In the sense of numerical simulation, this lockness, two-dimensional load lockness is very simple, easier. So he selected this geometry. However, he found that data does not satisfy constant wall hypothesis. So this is smooth wall, but two-dimensional load lock on the wall is strongly deviate from the similarity. So I want to say the 2D load lock on the wall is one of the special cases of general local walls. That is one of the equations. Because after his presentation of this data, when I attend any conference, always a strong debate. So this data satisfies constant wall hypothesis or not. Okay. And actually, that is my motivation in 4.5 important short law. Strong estimate to simulate this data, and I did and to them, and the same geometry as that of Drage, two-dimensional load lock in the wall, in boundary layer, not channel floor, boundary layer. And our data is not satisfied constant hypothesis is kind of strong interaction. That is the close-up data, this is our data, so not perhaps this hypothesis. So I think our data is more close to close-up data. And at the same time, Australian almost same geometry, load lock on the wall in channel flow. However, channel flow satisfies similarity very well. So that is the reason why the difference between boundary layer and channel flows. So this kind of load lock on the wall simulation in problem channel flow, JMS data satisfy constant hypothesis very well. However, boundary layer does not satisfy the reason. And back to my presentation, and then Polino and Schultz and Flag, they also selected the same geometry, two-dimensional. And then he found their data also does not satisfy similarity. So they were pretty much right at the time. And they conjectured, since 2D bar, load lock on the wall, height is in between, Q, not load the Q, and the mesh height in terms of delta. And the cubes have the same square axis shape of the bars. The difference between, I want to define 2D is load locum, 3D is this kind of cube. Are not due to size and square area ratio, because we use very small size of two-dimensional load local wall. However, constant hypothesis. I think they said, and the difference should be due to change from two-dimensional, three-dimensional element. So, sounds like due to blockage effect of two-dimensional load from the wall, the flow is very well. So, objective is just only in the last meeting, the meeting last year in Cambridge, I come to this meeting. I presented 2D data. So why this 2D data does not satisfy Walsh's hypothesis? So they asked me to simulate 3D. So what is the difference between geometry dependence between 2D? So that is our objective of this study. And DNS we did over humor of the world, and we obtained statistics, and we want to find the interaction between in and out layers, which are not satisfied founding hypothesis and segregation by layer. So we did an approximation. It's very similar to 2D. This is 3D true, and other things is very similar. But to describe this true geometry, we used most boundary method, and we used our own solver developed by ourselves. And this is smooth. So I will compare three cases. One was smooth zero pressure boundary layer to the local world. How much 3D local world, true world. So I want to use these three. So to do simulation, so inflow generation is needed. So because the periodic boundary condition along the streamlines are not applicable, so we need realistic common inflow data. And however, it is impossible to accurately generate turbulent inflow data over local no data. So DNS over local must use a smooth volume flow and then long time simulation in a streamline direction. So we're going to step change, from smooth to local, and to overcome this problem, streamlined domain size should be sufficiently long enough to the flow to reach a new local equilibrium state. That is I think smooth work. Okay, so this is 2D, this is 3D. If this side view is same as 2D, or the top view is also just chopped 2D. Because this is 3D. And the streamlined differences, PK over K is 8. So this is 8 times this 7. So the reason why
did you choose 8?
8 is
Why did you choose 8?
Okay, so Leonardi, they simulated, he changed the internal flow, several kinds of 2D, 2, 3, 4, 5, 6, 8. He found 8 is maximum. So I just follow his criteria, so we select the 8 PK in 3 minus direction. This is data. This is the smooth world, so long simulation of turbulent boundary layer simulated, and then step is starting. So very much unstable, transient, and then almost here we can get kind of new equilibrium state of reference. So we want to take data from this side. So this is already a process presented yesterday. So we used my data. And this is 3D, 2D, this is smooth work. So this is so the kind of under the thickness and momentum displacement. To friction velocity, we should integrate these two values, spin friction and friction from the lab. We also integrate all data. Then we use, and then also we use virtual origin from the zero. So we use Jackson's moment balance equation. That is mean velocity data. That is smooth wall. That is 2D rough in the wall. That is 3D rough in the wall. So I think we hope this really close to this here, but around here, but that is not why I'm not satisfied works in the hypothesis. And in the sense of velocity defect profiles, we can get very good similarity. This is Reynolds stress tensor U prime, V prime, W prime, and Reynolds shear stress. So as you can see, smooth 3D, 2D are not collapse. But not satisfy constant hypothesis. One thing is the Castello measured the internal boundary of this cube same geometry, but he used 3 minus we used A, but his data satisfied or simulated very well. So the 3 minus spacing, this value is one of the factor to satisfy or simulate hypothesis. So we select this one, so it takes almost 3 or 4 months to simulate this one. So we are now doing this value of 2, so we want to compare. So anyway, this is 2D, 3D, so all data is very similar. So flow characteristics are similar to those of 2D, although the values are really small. And you see the sparsely distributed cubes, A, is a little bit far from. And I think due to very strong plasticity, special effect, so it goes coming and emitting cube, and then due to plasticity effect, the flow is flow up. I think that is made usable. So we want to look at the light stage structures in the outer layer, how much difference between 2D and 3D. It is one of the things to find low moment LMR, low moment conditions. So as time goes by, so the strong low momentum lesion can be obtained. And so we also second packet structure we can obtain, we can find. And these large structures of local struggling with the same balance. This is 3D, this is 2D, this is smooth. So this data is very close to, or this is near the lower region. So as you can see, near the lower region, 3D inner layer of the layer is very similar. So LMR is very similar for 2D, 3D. However, the smooth wall, near wall is strict structure, but outside is quite different. So I think that this flow satisfies constant hypothesis, but this 2D is strongly integrated between inner layer and outer layers. So
these are instantaneous realizations.
Yes. No, everybody, yes.
Between what and what? I mean,
near wall and outer wall.
what is the black and gray?
Black is low momentum. Yeah, low momentum region.
Okay.
So high momentum region is high speed street, low speed street. And we also look at the elements of length scale. So this is smooth wall. This is the 2D or 3D. So length scale is slightly reduced, and so the conditional average of low momentum, for low momentum, not high momentum, so negative value is selected, and then you obtain length scale. And based on this value, the extent of LMRs are really decreased, especially smooth wall. This is Galilean decomposition of because subtracting the convection velocity, we can obtain 3D, 2D smooth wall. So that is one of the strengths So it's looks like a stick structure in smooth wall, but just need that is to roll the wall, the wall is blocked and blown out. It's 3D. And the inclination angle for smooth wall is 14, whatever 2D is 26, 24, so the floor is a little bit inclined upward. So we also apply functional averaging to detect vortex structure. So I use this kind of functional average. Also, we apply the linear stress extension. We obtain two-point correlation between velocity fluctuation and swirling strength. So this is 3D, this is 2D local work, this is smooth work. And this is the correlation of lambda CR swirling strength and U is streamwise fluctuation. So we can find the clockwise synchronized voltage we can obtain. So cross relation between inner wall and outer wall as compared with smooth wall. This is conditional average helping take motion and near the wall, swirling strength obtained. The impedance angle is also 13, it's very high. So this 3D case also the spring vortex head here and here is a little bit close for 2D 3D. For the smooth wall, your head and head is a little bit far from it with the 2D. So the three-dimensional spacing of the helping head is decreased for two faces as compared with the smooth wall is potential of a QT event. Ejection is associated with certain voltage also operate frequently in 2D or 3D walls with a strong correlation between inner wall and outer walls, outer layers. Okay, so summary. So I did the DNS atomic bundle layer for 3D cases. It's called pure lock and wall, and we take over 3D roughness. Also extended to outer layers, for example, by function hypothesis. Okay. So we check many kinds of data, instantaneous and statistics. Also we check the low momentum emissions in packets, how much the effect between inner layer and outer layers, and outer layers to the structure or is almost similar, not much different. It's quite similarity. So in the sense of Townsend versus similarity in log wall, the present DNS data does not satisfy similarity between log wall and smooth walls, which indicate strong interaction between inner and outer layers. Still, so this is compared to the previous findings of many previous data. They satisfy Townsend hypothesis. The special geometry load locking works. The main reason, as I said, is due to easy simulation. Very simple geometry for neural simulation is latest, but these two each LEDs still have a kind of special general roughness. The wall simulated criteria may not be universal for all 3D geometrical roughness. So numerical experimental studies with various pitches of small spacing and shape may be able to verify or simulate hypothesis more clearly.
So we have time maybe for one or two questions. Hassan?
I remember when Tim Nichols had the meeting in Cambridge, then we concluded, or at least the summary at the end of the meeting was that the two-dimensional roughness was kind of an anomalous or a unique case, pathological case or something like that. But you're pointing out here even regular three-dimensional roughnesses are also quite different than did I hear you correctly?
Yeah.
Well, this really complicates the situation in a number of ways, but I mean, maybe that's how we ultimately going to understand things. Would it be possible to do things where, like, for example, even the two-dimensional roughness is disturbed a little bit by small elements or something on top of the 2D, just to break down that transverse coherence, because maybe that's really the dominant.
Yes, yes.
Okay.
Splashing and flashing.
Yes.
Yeah, this is my need of 2D. Even though we use 4, but we can find very similar phenomena.
So
the
it's
problem is actually this 2D, 3D is from channel flow. That's it.
there's no difference.
No. In channel flow,
Yes.
the satisfied signal very well.
Okay.
Only difference on in boundary. So I think minutes say 2D, 3D, I don't know. From channel flow, boundary is totally different. In this case.
My question is not only for you, but also for a number of others like Ivan and Jonathan, who invoked Townsend's similarity hypothesis. Clearly, Townsend had in mind, please correct me if I am wrong, had in mind the roughnesses which was still small, and that's why he was saying that the outer layer would not have any great effect. An intelligent man like himself would not really say if the roughness extended to half the boundary layer, it wouldn't affect the outer region. So what I would like to see, in fact, is some measure of the influence of the roughness in the outer wall as a function of the roughness height. Let's say omega squared, mean square vorticity at y equals half delta as a function of roughness height. I mean, some such thing would be very much more useful for us to understand what the effect of roughness will be in the outer
I
region.
want to say, so use many kind of criteria to satisfy Townsend hypothesis. High range number and the roughness height is very small. Small satisfy very small. So not scale of that is 0.03. It's almost very close to what the roughness height is very small. Roughness height is very high. Strong correlation between inlet outliers, but even though very small strength, very small roughness height, and very high range number, but the state is not high range number, but the criteria of roughness, criteria for satisfying Townsend hypothesis made by him. So we satisfy his criterion. However, we can find this kind of phenomenon. So I think last year, Monty, high range number, small roughness in the world, even strong correlation, deflection between inner and outer layers.
I would like to see I mean, I understand maybe there is a threshold roughness below which the outside region is not influenced at all, although it would be hard for me to think that. So one should probably have some fixed quantity like a mean square vorticity, whatever, at y by delta half, let us say, because you're looking at the outer region. And I would like to know what the influence on such a quantity would be as a function of roughness height, for instance. And that would begin to get more quantitative. Maybe people already know this.
I've seen that people like Karen Flack have been doing things like that. And
Yes, sir.
I mean, at some point, she really gets these very small roughness.
Very small and
huge effect.
changes many kind
I
of
don't know
roughness.
what reason. But
Yeah, they satisfy.
I mean, in that case, they have higher than standards and they're looking at tiny things in there. I mean, she puts these crossbars which are very tiny and they just
So the only to the
One of the large things that you see is the difference in the angle of the structures. It goes from 14 to approximately double. But I guess this angle has to do with something with the deflactuations.
yes.
But the deflactuation is extremely with the friction velocity is about the same. It's not a big difference. So maybe actually the friction velocity is not the right scale in the outer part for the fluctuation. Maybe it's actually the U infinity that is the right scale. And then you would actually get this kind of then you have this kind of difference of a factor of 2 maybe.
Scaling down.
That would be scaling from that Utah is actually not the relevant scale in the outer region.
So generally, you're taking the rest of the scaling but so we can see that scaling.
Okay. You can thank Professor Song again. So the next
next presentation will be given by Carol Cossu of CNRS. And it's linear non-normal energy amplification of harmonic and stochastic forcing in the turbulent channel flow.
Hi, so this is going to work with Guillaume Bon. So you all know that if you observe what are the scales of the streets, in a turbulent flow, like a turbulent relay or channel flow, you have two characteristic scales, okay, one on the wall, one on the wall units, and the other one, large scale, which is like scales in afterlife. Okay, and the question is why these scales are selected. And then there is some inspiration from what is observed in laminar flow. Okay, so streets are created by a lift-up effect. So when you transform vortices into streets, and the amplification is large. And of course, is there a current lift-up effect in fluid turbulent flow? So this is one of the questions you can ask. Does it select the spanless case that you observe in the unforced flow? So the longest in the flow. Are the amplification large? This lift-up effect, like in the laminar case or not. And then if they are large, can you force these streets to control the flow, okay, in an efficient way? So these are the kind of question that we so in the laminar case, one way to control the flow in an efficient way is to force streets. Okay? So the optimal perturbation, when you do transition, they are bad guys, okay, because they amplify energy that lead you to transition. If you do control, it's something good, because you amplify a lot the energy of the actuator. Okay. So the question is, can you do the same in a turbulent? And then the classical approach, that's the classic, the recent approach, is been taken to study this kind of side, is to take the turbulent base flow. So you take the turbulent mid flow, for instance, okay, with the region, and so this is the Reynolds-Tiedemann profile, okay, with and then you perturb it a bit with current perturbations, so small u. So u is the base flow, parallel line, small u are the perturbations, and the action of the decorrelated motions, okay, you prime, everything goes into a Reynolds trace, and then you can simplify it out, okay, we try to do it as simple as possible, put an eddy viscosity, okay, to move on. This eddy viscosity is in equilibrium, of course, with the and then you assume that the perturbations, the coherent perturbations, are small. So if you do that, you neglect the nonlinear terms, small u equal u. So this has been used in Reynolds cosine, okay, to interpret experimental data. Javier Jimenez and Delala have used it exactly in that way to do stability analysis, okay, normal stability analysis. And so what do you find? These profiles, what you find, they are linearly stable, okay, if you use this approach. And then you have to explain why these streaks are amplified, and it's by no. Okay, so what people do, sorry for the probably already. So first is a linear operator in the plane is homogeneous, so you decompose in Fourier modes, okay, alpha, so string-wise wave number and span-wise wave number. Then you inject this in the equations. You have incompressibility, so you can reduce, instead of having 3 velocity components, you can go to 2 scalar quantities, one on velocity or vorticity, so you form a state vector. You can go back and forth from the velocity field to the state vector, and from the state vector to the velocity field with a linear operator. You do that, you inject in the equation, and you end up with in control theory, this is like a plant, and then you have the actuator of the forcing. Okay? So, and this is an evolution equation. Okay? So if you put a body force, here is the state, and inside A, you have a generalized orthomorphic operator, a generalized square operator, in which you have the base flow. Okay? And get viscosity. So you do that. And then the first question you ask is what are the optimally amplified initial conditions? So you put a 0 forcing, so the problem is not force. You give an initial condition, U naught. Okay? So this U naught will become an initial condition of the state vector. You integrate the simple linear system that I wrote before. So it's Okay, so in this case, you have no forcing because it's a linear equation to get the solution. you convert it back to U, and then you can answer this kind of question. Okay, so you solve your problem, and then you can maximize the output energy, changing the initial condition. Okay, at T equal T naught. If you maximize that, you call this a scalar, so this ratio, this optimal ratio is the optimal amplification, and it's the norm of this operator. Okay? And then you can there's a function of T, and then you can maximize over all possible times, and you get the optimal, the worst case or best case.
Your A has eddy viscosity in this.
Yeah. I need dissipation. Okay. I put inside. So the ingredients are the mean flow, so the shear at every time. So it's a real shear, and then I need the dissipation, and then dissipation is the eddy viscosity. So I put this in the model, and what does the model give? Okay. So you can do a uniform shear, but here is the precise one. No? It's the one that. And then this has been done by the Lara Jimenez, and then after this is the channel flow. So the most amplified structures are stringwise uniform. Okay, so you find the G max is for alpha equals 0. Okay, lambda x infinity in the stringwise direction. And then if you look at the spanwise, okay, most amplified structures, you have so this is beta. So the spanwise wave number. This is G max, and you see that you have two peaks of amplification. One, which scales always in outer units. Okay? You change the Reynolds number if it is sufficiently large, it's always the same scale. Okay? And then when you look at the structures, so the optimal initial condition are vortices, there are in all the channel, and then the optimal response are these streaks. Okay? So this is a high-speed streak, this is a low-speed streak on the other side, okay? With a spacing of or h. These are the most amplified. If you go here, there is another peak. When you put this in wall units, this is 92. It depends on the base flow you have. So it's around 100. And again, if you look at the structure, now you have to plot this perturbation in class units. Okay, you have Y class. The optimal perturbations are stringwise vortices at a height like 15 wood units, and the optimal response are streaks something like. They do not change. When you change Reynolds number, these two peaks, okay, we go the inner scale peak will go the further distance, but the amplification and this will not change. For the larger scale peak, when you increase Reynolds number, this amplification increases. Okay? In between, you have no scales. Okay? And then you have self-similar structures. So the only scale is the spanwise wave number. Okay? So outer scale, inner scale, and then spanwise wave number. So, but this is for the initial value problem. So the question is, what happens when you consider a force problem? So if you want to do control, you put a body force. This is a deterministic forcing. So, okay. So what is the response to forcing? Or if you want to study, for instance, in a turbulent boundary layer, what is the influence of free-stream turbulence? We have seen that. How does free-stream turbulence force the response in the boundary layer? You will put a stochastic force. And then you can also interpret this in a third approach. If you want to model the scale interaction, okay, of different scales, they can be not correlated at different scales. So you have the nonlinear term can be seen as the action on a given alpha beta structure of the other scales. So you put a stochastic force. And of course the question is, do you have the same double peak structure of the response or of the amplification? So we have done a previous study in the turbulent quite flow, but a very low Reynolds number in which you don't have scale separation. Okay, so we cannot conclude about this. No? So you have redone everything on the So in this system now, okay, you put F is different from 0, you put it like an harmonic forcing, so this is 4. The operator A is stable, so you wait long enough, you have an harmonic response to this harmonic forcing. That's it. You inject this in the equations, okay? Before, so you put a tilde, the time derivative becomes I omega, okay, minus A. So this is and then you go back to the velocity space, from the state space, and this is a transfer function, okay? Or this is the resolvent operator computed on the imaginary axis of the complex plane. This is a complex number. And then you get this simple transfer function, and then you do the game again. The game is, what is the optimal output how can I optimize it as a function of the forcing shape for this given alpha beta Reynolds number, and you call this the optimal response to forcing. Now it does not depend on time, it doesn't depend on frequency, okay? It's the norm of the transfer function, and then you can maximize this again over weekend. Stochastic forcing, Now you put the body force is non-harmonic, is stochastic, delta correlated, is a caricature, okay? It's oversimplified. This is not a realistic forcing. It just is a stochastic. It's just to see what comes out from the operator. The input is not realistic, and with this non-realistic input, we check what's the output. Okay? And then you put this inside, and then you ask what is the variance of the output. Okay, if you have an input with a unit variance, is it amplified a lot or not? And then you can get this. This is the classical theory. So you form the covariance matrix. You can form it in the temporal domain. Okay, with this operator X is a solution of an algebraic Radionov equation, or you can have it in the spectral domain in time. So you can integrate H times the transfer function as the joint in omega, and you get this. You get the trace, and this is the variance. Okay. So the question is, what's the output? Okay, what's the response? So when you do the computation, okay, this is again is beta H like before. This is the response R max. So the response to harmonic forcing. This is the response to stochastic forcing as a function of the for different string-wise wave number alpha. So what you observe is that the most amplified alpha also here is alpha equals 0. Okay, in the two cases. When you increase alpha, you have a lower amplification, but if alpha, okay, if the string-wise wavelength is bigger, larger than the span-wise wavelength, then you get almost the same. But what is, are there two peaks? No. Okay, we see, of course, so you inject energy, but this is dissipated at different rates, and then you have like, you have this amplification, spectrum of the amplification. And what is there is an approximate, so if you do this in another block plane, you say, this is a dependence like beta to minus 2 in this region, and you have a change of slope around this wavelength, lambda plus equals 80, and you have a maximum here, a very large scale. Okay? And for the stochastic forcing, you have a different dependency, beta to minus 1. Okay? So the question is, if we want in between, if you look, there are self-Taylor structures. So the idea is to detect these two peaks. Maybe we have to plot not this spectra, but the deviation from this power law regime. Okay, so what we do, we pre-multiply these functions by beta squared, and this what. And then what you get is exactly like for Gmax. So you get two peaks. For the two, they are very large amplifications. The first peak is at 3.5 H, okay, in good accordance with what you see in the spectrum. For harmonic and stochastic forcing, you have a second peak around 8. In between, there is this region. So you can have a debate if Reynolds number goes to infinity, this will be a plateau. Or you have again an influence of these peaks inside. We don't know for the moment. If you do a rough estimation, you should go to Reynolds tau from 6,000 to 600. You have to go to Reynolds tau 600,000 to have 2 decades. To hope having 2 decades of this plateau if it does exist. Okay? Now you look at the optimal, the perturbation corresponding to the two peaks, okay, a larger scale and small scale. And you see this is the optimal input profile, okay, of the hat function, okay, so where you have the maximum of the vortices, this time as well, you plot it. So this is the whole normal profile of the optimal input vortex in the larger scale peak. So it's a vortex which is about the wall, it has a maximum in the center of the channel, and then it goes to 0 back. The response at larger scale are streaks. Okay, they are 0 in the center of the channel. They have a maximum at the edge of the outer layer, and then they go to the wall. And then in this region where they go to the wall, they go like the mean flow profile. Okay, so they have 50% amplitude at y class equal 12. Okay, they strongly penetrate to the wall. So this means that you force the stuff in the center of the channel here, and you get a response which is amplified by R max, 10 to the power 6, at y class equal 12. So this can be useful for control if you want to explain how you influence linear wall motions. If you do the optimal for the inner peak, that's okay. That's the same. What is amazing is that you do the tree analysis with Gmax, okay, in time. Harmonic forcing or stochastic forcing, you plot the optimal functions. In stochastic forcing, you need to do the most correlated functions, so the PLD modes or Carun and Loewe functions, and then you plot them. They are the same. They are the same. Exactly. The three different approaches lead to the same optimal functions. Now the question is, can we explain why we have beta to the power 0 for Gmax to the minus 1 and as a function of beta for alpha equals 0? And the first remark is that you go in this approximate power law regime, you plot the optimal input and the optimal output for different spanwise wave numbers in this regime. They are almost self-similar. Okay? So you can assume that if you want to explain this behavior, you have to take geometrically similar functions. So if you change beta, they will be this is y over the spanwise wave number. Okay? So this means that these functions are something like that. So if I do a section, for instance, of the vortices, you have the wall, you have a given spanwise wave number, lambda z, and then for this you find two vortices which are like that, with a given shape. Okay? So yeah, they have a maximum at a given distance from the wall. But now if you change lambda z, this means that they keep the same shape, okay, and you just rescale. So you take a smaller lambda z, and then they will have the same shape but rescale. So you have a similarity variable, which is y over lambda, the spanwise wave number. So this is y times beta, wave number. You can, okay, you assume geometric similarity, so you have a similar set vector. Then you assume that you are in the log layer. Okay? If you look at these functions, you do this in plus units, the maximum is in the log layer, they decay in the log layer, and then they just need to go to the wall. So you assume that the eddy viscosity and the U profile, U prime, the shear, are log layer. So they also rescale because the eddy viscosity in the log layer is U tau times K times Y, or it goes like this K. So you can assume similarity on Y and you get this function. You inject this in the equations and you get rescaled equation in the rescaled variable. This stuff here. In which beta is the ratio, so you do all the computation at the reference beta, okay? And then you change beta and you ask for the new beta, how does it compare the result to the one that you have computed on this beta? So you do this, you rescale the time, and you get this rescale system. But in the rescale system, the only dependence on beta is here. Beta to minus 1. All these operators are the one computed, for instance, for this reference case. Then you change it. You squeeze it, and then the question is, so you have that. Now, what
reference case meaning unforced case?
No, the reference case is, what is the reference case? This is a good question. So I have G max or R max or whatever, they have a dependence on beta. Okay? Then here you have a large scale peak, and then now I take, inside this regime, I take whatever beta I want, and I compute the optimal amplification G max or max for this beta. Okay? That I call beta. This is the reference case, and then I change it. Exactly, sorry. If I do this, I have the rescale equation. If I recompute G max is the norm of this, but you see, in the definition of G, nothing depends on beta, just the time. The time depends on beta. So this means that the optimal amplification in time does not depend on beta. This is what we found. So it's beta to the power 0. And what depends on time is the time. Okay? You have to rescale the time at which you reach the maximum amplification. If you do that, you see that the maximum dimensional units now. The time of maximum amplification is inversely proportional to beta, so it's proportional to lambda. And this is what has been observed by Delara and Jimenez when you do the optimization. Okay? So the time of maximum amplification is proportional to the spanwise wave number. So this. Now you do the forcing, okay? The optimal harmonic forcing. You will do the same. You will scale the transfer function, and then the transfer function. So you have this kind of dependence, and then you have this beta minus 1. This beta minus 1 comes from the beta minus 1 here, okay, in the fourth term, in the rescaled equation. Okay, so when you do the norm of this to the square, you get that R is this value, which does not depend on beta, times beta to the minus 2. So you find again what we have found from the computation. So you do this for stochastic forcing. The only stuff to understand here is that you will do this, you can compute this with H, and when you put H times H adjoint, you have a beta to the minus 1 for each H, so you get inside a beta minus 2 dependence. But then you have to integrate on the frequencies. But this function H depends on the rescale omega, so you have to rescale also this omega, so you lose a beta. And then you have a beta minus 1 dependence.
This is still delta correlated.
This is still exactly fine. No. So what are the conclusions? First, is that if you do this kind of analysis, you have an approximate. Of course, there can be a Reynolds tau dependence, and D delta. As long as you, if in the base flow you put a log layer, then you get this covered origin in which you have geometrically similar structures. Okay, this is Townsend. This is well known, but now it comes as a result. Okay, we do nothing, we just optimize it, and from the optimization it comes out this geometrically similar structure. If you have two peaks, okay, you have two peaks if you pre-multiply the response to force in the right way, beta minus 1 and beta minus 2. They are at the same length. The force response, stochastic or harmonic, can be very large if you force a large scale, and they can go very deep inside the boundary. Okay, so you force in the outer flow, and then you have a large response, and then we find exactly the same optimal perturbation for all the frameworks. So we don't know if this is new. In the laminar case, we have looked at the literature, and we have not found. So is this a coincidence, or so this is what we have needed. And this is the reference to the one. And what we're doing now is to extend this analysis. Okay, so this scaling applies when alpha is equal to 0. If you assume that alpha is a small component to beta, so there are stringwise elongated structures, okay, with lambda x finite, not infinite. But it seems that it carries on. So if you have large elongated structures, you get the same kind of behavior of scaling. In that case, this would mean that you have a k minus 1 law inside the log region, and this is an argument of controversy. It's made, but we get this from the equations. Probably. So this is under, and then the question is what is the relation between this stochastic forcing analysis, which is not realistic, and the scaling that we get that looks like what is observed. Okay, so thank you very much for
We're going to have time just for one question.
I'll probably expose my ignorance by asking the question. As I understand, you say there are two separate scales of street, like structures. One of them large scale, one small scale. But the mechanism for their existence and growth is exactly the same. That is, they are really coming from the non-normal growth transient level. Isn't that what you're saying?
Yes, that's it.
So presumably these large-scale streaks are related to these very long structures that people are talking about. Is that possible? Is that what you're saying?
Yeah.
But the time scales for the two of them must be very different. Where does it, I mean, the large scales presumably take a long time to grow. The small ones take a very small time to grow. Now, I don't see, because they're both transient growth problems, I don't see where the time scale comes into the problem.
It depends on which problem. So if you go in the problem,
the same
in
problem
Gmax, it comes from the optimal, the time at which you reach this optimal amplification. It's just like lambda.
And what is to say that within the time scale it takes for the large structure to grow, the small one remains correlated somehow? You see, you are trying to make a connection between the large and the small, but the time scale for the large one is long, and during that time the stuff at the bottom might change a lot.
No, here I take alpha and beta, and I say that if you do an analysis scale by scale, there is no interaction, it's linear. At this linear level, okay, this is small scale.
But when you talk about control,
they grow and then they go down. If you superpose them, which is probably they will interact, then of course you have this population of small scale stuff that goes on and dies and then regenerates very quickly. And the other ones, they will have a time scale which is longer. This is what is observed.
But my question was, in the control part you were saying somehow you try to control the outer structures,
okay.
And you begin to control the small ones too. Okay, maybe I should talk to you more. That doesn't make sense to me.
Maybe we'll leave the discussion for lunch. Thank you again. So the next talk is given by Beverly McGill of Caltech, and it's entitled Critical Modes in Turbulent Pipe Flow.
Okay, thank you. This talk will actually follow really nicely from what Dr. Wolfman's been doing here at Norwegian. And I thank Dr. Wu for the use of his DNS data from the pipe. I ask you to consider the full turbulence field in pipe flow. We're going to look at a decomposition that's harmonic in the streamwise and azimuthal direction, so streamwise wave number k, azimuthal wave number n, and give it a harmonic temporal dependence omega as well. So we're going to look at oblique propagating waves in the pipe. And then just as a nicety, we project onto a divergence-free basis. Necessarily the kn omega mode equal to 0, 0, 0 must be the turbulent mean profile at that point. So we can do this decomposition. We can write Navier-Stokes in this form because we're in a divergence-free basis. So this is the temporal dependence of the velocity field, the linear operator, and then the nonlinear terms we lump into the forcing term f here. And we will use experimental data from the superpipe to give us that turbulent mean profile. So this is very similar to what Carlo showed, except we're looking now at a specific kn omega combination. And we're going to use what we know about the turbulent flow to examine kn omega combinations of interest to turbulent flow. This operator here, because we have the omega decomposition, we can expand the v dot term, so just as Carlo did, we have this operator, the resolvent. And if we take a look at the form of the resolvent, for the way we've set it up, you see it has this form here. So this is the term, the interaction of the radial velocity component with the mean shear that's usually attributed to the non-normality of the linearized operators, usually attributed to this. However, you see that there's another way that you can get a very large or almost singular response of this in terms of the resolvent here. At turbulent Reynolds numbers, well, in turbulence, the Reynolds number will always be large, so A is an operator. This term will be small. And you can get essentially 0 on the diagonals if k times u, where u is the local mean velocity, is equal to omega. So basically, if the mode that we're looking at is critical in the sense that there is a place inside the pipe domain where the propagation velocity, the streamwise convection velocity, is equal to the local mean, then this operator, this resolvent, will have a large magnitude, and this is basically an input-output relation, input-output relationship, just as was described in the previous talk. So this is a piece of work with ARTI to appear. And we then proceed to analyze this operator and determine the forcing mode shapes that lead to the maximum response using singular value determination for this operator. Before I show you some results from that, let's just take a little further look at this operator. If you look very closely at it, this is written in terms of the free velocity component. I could equally well have written it in terms of a wall normal velocity and a wall normal vorticity, in which case it looks very, very similar to the Orr-Sommerfeld operator, just with the turbulent base flow at this point. And we know from the Orr-Sommerfeld equations, and you can go through and do the same analysis here, it's identical, that there are two, first of all, in the Rayleigh case, there are two inviscid solutions. The two additional solutions you get from the Orr-Sommerfeld equations require viscous effects in two places. So the first one is close to the wall to meet the boundary condition, and the second one is to avoid the singularity at this critical layer, where the convection velocity or the phase velocity of the mode is equal to the local mean. And this is very similar to something in Schmidt-Henningsen. You could see that if you consider a linearly unstable parallel flow for now, so let's make it simpler and consider a channel. If you consider the neutral curve in channel flow, you can see that there would be two solutions, an upper branch and a lower branch, and the wall layer here, as I said, meets the boundary condition. In the upper branch, the critical layer is distinct from the wall layer. In the lower branch, they overlap. So the hypothesis here is that for the linearly unstable case, we're thinking about the eigenvalue spectrum. In this case, the mean profile is linearly stable, so we're thinking about a pseudo-spectral argument. So the hypothesis is that the same physical effect, as you would see with the in a linearly unstable flow with these neutral waves is manifested as a high system response to forcing in the turbulent case. So if we focus on the lower branch, we see some interesting things that I'll develop. I won't have time to go very much into this, so I'll be happy to talk about it afterwards. But we would expect two things. So first of all, the wall layer and the scaling gives you that this must be centered on a y plus of order r plus to the half. And you would expect the critical layer centered on y plus proportion to r plus to the 2/3. Now there's a k dependence in there too, but this is the general scaling. And interestingly, some earlier work by Srinivasan and also some work by Sirivec et al. Has pointed out this general critical layer behavior, and they were able to show that the shear stress in internal flows, I believe, scales with r plus to the half. So that's consistent with the wall layer concept here. The critical layer idea, Sirivec mentions this possibility of wave-like motion further from the wall. There's an interesting consequence of this lower branch, which is that if the critical layer reaches down to the wall, and we've been talking quite a bit about things that are further from the wall, the long region that reach down to the wall and seem to have some modulation effect on the smaller scales, or have a large footprint down to the wall. In this setup, the wall layer has to respond to meet the boundary conditions, so there is necessarily a coupling between what's going on in the critical layer and what's going on in the wall layer across scales. So this may be some explanation for some of the amplitude modulation effects that have been explored recently. So now let's go back to the model. So what I'm going to do is take a look at the first singular mode, or rather the mode associated with the first singular value of this operator. Singular values are large, so there's a large amplification of the forcing that arises from the non-linear interaction between other combinations of Kn and omega. I'm showing you here what happens if you increase omega for a fixed K and N. And this is K and N of 1 and 10, so I'll focus on that a little later to talk about the very large scale motions. And this is a cross-section of the pipe, looking at the distribution of total kinetic energy. So as you increase omega, you're holding K constant, so you're increasing the phase velocity of these oblique propagating waves. You can see that the distribution changes slightly, but the mode stays attached to the wall. And then as you increase omega even further, the mode detaches from the wall and moves towards the core of the pipe. One can trace, this was kinetic energy, but it's mostly dominated by the streamwise velocity, particularly with the lower omega. So if you trace the location of this kinetic energy U peak, as you increase omega, and I've picked here two particular wave number combinations that we know to be of interest in wall turbulence. So the first one would correspond to at least approximately the near wall streaks, the second one to the large scales. So we've got Y plus here, and then U on U center line here, and it's not coming out really well, but there is traced in here the mean velocity profile at this particular Reynolds number, or these particular Reynolds numbers are different. And what you see if you focus on the solid black lines first is in each case, as you increase omega, so as you move up the plot, the Y plus location of the peak energy doesn't really move very much in Y. The mode stays attached to the wall. At some point out here, the convective velocity is equal, so that the location of the peak energy is equal to the local mean velocity. So from that point on, the peak energy moves, the convection velocity of the mode is equal to the local mean velocity in the pipe. So we would say that our model here then is predicting that the largest amplification occurs for the wall modes here, for low omega, and for critical modes here. And for this mode, something corresponding to the VLSM type wave number pair, that transition occurs when the phase velocity is 2/3 times the central line velocity. So I'll come back to that. I have time. You can get some interesting results, such that for the near wall peak, as you increase Reynolds number, you see that the mode is focused around a Y plus of 15, the U plus peak stays there, that's a wall mode. You can approach alpha scaling. If we take a look at what the mode actually looks like in a very large scale motion, this VLSM-like mode, so K and N of 1 and 10, and a phase velocity of 2/3 times the center line velocity. Remember, that's the special place where the mode has the characteristics of the wall mode and the critical mode. You see a distribution like this, so it's oblique, so U and W look kind of similar. This is an interesting feature that seems to appear in all sorts of flows, that as you get further from the wall, you lose the spatial phase variation. You see something that's quite in phase. The interesting thing here is that V is very different. There's no spatial phase variation. If you look at shear stress, and if you were to integrate that, you will see that the shear stress contribution would be local, so this is consistent with attached eddy type hypotheses. I should say the way we've set this up, this should be familiar. It looks a lot like a wavy wall, response to a wavy wall, and that's as a result of the way we've set up the problem. So you can use this idea that the VLSM has a phase velocity of 2/3 times the center line velocity, sits in the log layer, so you can write this expression, and predict that the peak energy associated with this mode should scale with R plus 2/3 with this constant, and the data from the superpipe support that very well. So this is our theoretical prediction, the dashed line, and then the dots are results from the superpipe. If you superimpose a left and a right going wave, you end up with this kind of picture in the pipe, and this should look kind of familiar to something that Ivan showed when he was talking about the structure of the very large-scale motion. So showing lozenges of plus and minus velocity. These are isosurfs of U. And if you compare to what's going on in the visualization of Monti et al., I can convince myself that these very long structures here are a visual trick. You're joining these lozenges with other scales superposed. Okay, so moving on to John Liu's work. He has taken the DNS, pipe flow DNS of Wu et al. At an RE tau of 680, and we're going to try and project this onto the modes, these critical modes from the model. So if you integrate the axial velocity spectrum in R, see which are the dominantly energetic modes in the pipe, you get something like this for one realization. You can do it for many realizations. And you can see that there are hotspots. So there are modes we should be concentrating on that are energetically dominant in the pipe. So the method here is a little tricky without the time information, but basically we can get to, for a particular K and M, we can find an omega that gives us a maximum correlation in a given K and M in the pipe. Then we can adjust the phase, the relative phase of our mode to what's in the pipe. And then we get the amplitude by minimizing the difference between the critical mode and the DNS. So that gives us everything we need to know about the critical mode. So here's an example for one of the most energetic modes in the pipe. What I'm showing you then is the magnitude and the phase of the complex velocity at a particular K and N. And this is the distribution in Y. And this magnitude is such that if you integrated, summed over all K and N, this would be correct for the total energy in the pipe. So the red line here is the prediction of our critical mode, this is the phase. And at this energetic mode combination in the pipe, our one critical mode cancels 78% of the energy at that particular K-N combination. You can do better. So John looked at several different omegas, and with 6, you get up to 95% cancellation of the energy at that particular K and N. And if you take a look then at the integrated axial spectrum, this is what we started with, a total kinetic energy in U. This is not full TKE. If you look at what happens when you subtract those now 9 of the most energetic modes, here's the picture. These hotspots have gone, and we've had a total reduction of energy of 6%. The top most energetic 9 modes on this picture were 66% more energetic than the 9 most energetic modes after we've subtracted these most energetic critical modes. So I would say that if you were to do a POD analysis of this data, this was done by Doug, well, not this data, and lower Reynolds number data, Doug et al. Did this for an RE tau of 150, 9 modes would give you a total reduction of 12%. So we're in the same ballpark, we're also at a higher Reynolds number. The POD modes are optimized for energy reduction, and we're doing this without the time information. We'll be able to be a lot more accurate in terms of omega if we have time information. Okay, I'm going long, so I will briefly go through the conclusions. So we were looking at oblique propagating modes. We can explain with our models several results from the literature, including some prediction of how the VLSM peak should scale with Reynolds number. And our preliminary analysis performed by Jean Liu of the type flow data of Wu et al. Reveals that these modes that we're predicting seem to dominate the integrated span. So thank you for your attention.
We have time for a few questions.
You said the velocity of the critical layer is multiple 2/3 or something of the pre-stream velocity. Isn't that what you said? Actually, when I looked at it some time in great detail, I found that the velocity divided by the pre-stream would be some fraction like 2/3 plus some u star by u infinity kind of thing. So there's a slow correction on that, and I wonder if you look at all your data more carefully whether it's consistent with a u star by u infinity correction. In fact, I saw you have 3 points and 1 point going down. Maybe it's actually not inconsistent with what I'm saying. Yeah, for instance, I don't know. Maybe
I indicated here that spatial resolution is a problem, so I would say that one is low from a measurement region. That 2/3 only holds. So the 2/3 only holds for a k of 1. So there is a wave number effect. So if you look at the full field, you would get something different, which may be yeah, so this is only for the VLSM.
I understand if you put all the nonlinear term into the Poisson term, but anyway you are handling the same operator like parallel, nanu, and butler and parallel. And then in their work, they put some time scale to find some sort of the length scale selection problem. Or in the later paper, in the case of the ladder, when they handle ladder one, they put some constraint in the omega. But in your case, I think you just pick some combination of the alpha, beta, omega, and then you just compare with the heuristic tolerance flow. But the operator doesn't provide any length scale selection principle. So for me, it seems to be a little bit arbitrary.
Well, it's exactly the same approach that was made in a previous talk, which is that if there's a component of forcing in that direction present, you will see it because it's so strongly amplified. The benefit of doing it this way is you're actually picking Kn and omega that you know is present in the turbulent flow. So omega is constrained, such as the phase velocity is what you would observe. The K and N are real. You could observe them, you could force them, so I get time to talk about it, but just to convince you that I'm still an experimentalist, if you consider distributed roughness where you can pick lambda x and lambda z and omega, and you can vary them, you can actually force these modes, both in GNS and in an experiment. So they are real, you can force them, and I would say that this is a much more realistic way to approach a turbulent field because it's actually, you're in the range of what you see as a flow.
Yeah, I understand, but what I'm saying is but this operator doesn't provide any length scale selection by itself. You choose. You can choose whatever you want.
No, but the point is, if you have the correct modes, then your forcing term is correct, right? If you take a foot, this is basically a DNS decomposition, right? So the u dot del u that gives you the forcing. If you have all the information, that's exact. So we are approximating that, and the results speak for themselves. We can predict the output of turbulent field. So
okay, thank you.
I don't know what else to say to that.
I have two questions. The first one is the scale you showed there. Is that somehow related to the fact that I think the bulk flow velocity is exactly the same as the velocity if you're a quarter away from the wall? It exactly matches it. I mean, if you look at Lex's data, you plot them and you compute the mean, and you divide it by the mean, I think, you see that they all collapse on that one point, so that is a
Yes, it's a quarter.
a quarter of the radius, or the
Yeah.
3/4 go from
That's a very good question. I mean, I think it's all, so as per my answer to the last question, it's all linked. So if you have a consistent set of modes, then and the other point I should have said is if you have a consistent set of modes, then you will also regenerate the correct mean velocity profile because you have the right shear stress distribution. So it's probably buried in there, but I can't answer that immediately.
Right. And the second question, looking at Lex's data, and I actually published that in a 99 JSM paper, there is this, I mean, extremely good power law of the core region. I mean, it's in between the center line and say 80% out of it. If you do defect scaling, I mean, the data of Lex's superpipe essentially completely collapse, and also you can see that in some data Hendrik has now, also for the rotating pipe. There's this extremely nice power law, Hendrik. Well, you're not going to show that, right? But I mean, it's almost perfect scaling there. Can you comment on that from your analysis?
To do with this? No, I can comment on it to do with my earlier work with the pipe, but no, not to do with it. Like I said, if you had the right selection of modes, then you would be able to regenerate that. There's information on both sides in your observation, in the form of that profile and in the mode shape you can predict, but we can't put it together yet.
Okay.
So it's very dull.
Thank you. So the next talk will be given by Masaharu Matsubara, and the title is Skip Friction Measurements Using Towing Tank Facility. Okay, I can start. This is a large collaboration with Nagoya University, and there are many people working on that. Many students actually. That's Mori and Imanish, and also the Hattori, and also we also have one or two students from CC University, and some other university also taking care of some data estimation. Also big help in the Kyushu University to use the Kyushu University towing tank. So it's a pretty large group to make this experiment. And fortunately, we have many towing tanks in Japan because of the shipbuilding company. So, and one is for that the really ship to measure. Shipbuilding has the towing tank for the drug measurement to estimate the fuel consumption. So usually very important. So they need accuracy of 0.1% of that to estimate that value. And in that case, very careful experiment facility they have. That's the wave reduction here, and also very accurate towing curve. And also in university we have some, and this is in Kyushu University. And length is pretty short, but still we have a 65 meter. Depth is quite enough. Wide is 5 meter, more or less okay. And velocity also still we can go up to the 3 meter per second. And also we have a very big towing tank. This is the largest one in Japan. This is 400 meters and 50 meter per second of speed. But usually quite this towing tank is busy, so I couldn't use that. We couldn't use this one, but instead of that, we use this one at the end, but we couldn't get good data. So actually, mainly we used this Kyushu University experiment, and for the prototype model we used for this tank. And actually, plate we can talk very long, but we can start like a 1.7 meter and take like a 50 meter if we can build that plate. And velocity, it depends on how, but it's not so difficult to do that with 3 meter per second. Maybe possible 6 meter per second. If you take these two values, the Reynolds number is REX is like 9 to 10 power of 6. So if you calculate, this is kind of parameters map, but this is 12 meters point and plate. So not this one, this one. Yes. Oh no, this one. Sorry. It's just simple. It's going slightly larger than the wind tunnel, and but still Cyclops is this green line, so cannot compare so much. But if you have like a 80 meter film, you can make this value. But this it's not so easy. And there are many experiments even in the early 20th century. And there are many actually, we put it just three names, but actually that one Japanese did quite many experiments. And also Shanghai did, Temple did use very large model. And actually recently, you can say, in 1986, the KDH group made some similar experiments. And Kalman-Shanghai's Shanghai formula is starting with this equation. And he just derived the local skin friction from this and this one. I'll talk that. So Shanghai used this plate. It's big, okay. It's 60, like a 5.4 meter. They have some beam here to treat the boundary layers. And it's a quite nice idea because he measured this structure independently, so he put the substructure with draft. And this is the recent results. This is locus description. And Shanghai, the formula is pretty large, especially the large Reynolds range. Reynolds number range. Yes, and just going back to the Kalman-Shanghai's formula, he started with this formula, and we have the Kalman constant here, and we have some constant m. But Kalman neglected this m and just using this k, and might be this m is very small. It's not really sure. And he got this number 0.39.5. And actually he did this experiment. This is Kemp's experiment. And he took this line. And we use several actually. One is the small one. This is just the testing. I did like 3-4 years ago. And we made wood one and aluminum, and actually we extended this plate C at the end of the experiment, and we gave up to measure the total skin friction directly, but we tried to get the local free skin friction. The experiment is very simple, but we should be very careful to measure drop, because actually, even if larger plate, it's the drop is quite small. Sometimes less than 1 kilogram force, so quite small. So we floated all facility like that, and we just connected the load cell here. We could measure. So this float just gives this force, vertical force, and they never affect that the load cell measurement. Yes. Just moving like that and take it. Yes, this is the raw data. We started from 0. We have some offset, but we subtract these values and go down. And we have some pretty large constant time. It's like more than 20 seconds. It also depends on the velocity, but we had like 10, at least 10 or 5, maybe 5 is the minimum to get this data. Actually, we can see some small vibration here, almost constant. And it's very noisy because it has a vibration. So vibration, load cell can pick up any vibration. Yes, first we did many, but one of the experiments, we use the without sharp edge as tail, so have very large drop or skin friction. And if we taking, we put the sharp edge at the end of the plate, we have the pretty nice data. But still, there are many friction coming, of course. One is the way making a drop, and also tripping wire has some drop. And the pressure also, we have a pressure distribution at the leading edge also tail. And also bottom, we have some drop. So, what can we do? That we start to change the drop. So we can neglect bottom effect. That's one here. And we subtract these two forces, we can get some area of the drop. And we tried to do that, but still the other drops is from tripping wire and leading edge pressure distribution effect so much. So we give up to measure total drop, and we added some one or two plates at the end of plate. We also can subtract in the X-ray. And this is my little complicated calculation, but it's very simple mathematics. It's just subtract all of them. Then we can get the real value of CF. And this is local skin friction for FCN. And this is Shenha's formula, but and this is our data is a little bit smaller, so that would be nice, because if you compare with the others, they have a smaller value. So this blue line is ours. So we got more explore to the extract data, and also that the floating measurement in this is the 6% difference. So between the Palman shape, the order of 1%. and people are very hungry right now, and I don't put the conclusion very simple. So we got to this equation, we can estimate Kalman constant from this. So we got the 0.37 or 38, I should say. So it's not too bad. Thank you very much.
We have time for questions. I mean, do you take into account the transition region here on the matrix also?
If you subtract the extension,
Yeah.
it's automatically subtract that area.
Is there any indication that m is different from 0?
That's I discussed with Tsuji yesterday. Actually, we don't know so much, so we didn't test. So m is not really. It's connected to b plus b0, but not directly. So it has some more constant.